Thank you, sir.
Mhm.
Okay, so today we are going to go over writing in the margins, which is a paper by Writer AI. Actually, I can actually just open the paper itself over here, I do believe. Yep. Um, which is primarily like an inference time technique to handle a variety of issues. Better inference pattern for long
A long
context
weekend.
retrieval as
Yep, yep.
described.
Thanks.
Um, so we have also, yeah, please feel free. I tend to like get on a roll and start yapping in a bunch of random directions. So if anything occurs to anybody or you have comments or questions or whatever, always feel free to jump in and stop me or whatever. Um, but now this thing is can I hide this perhaps? Hide video, hide floating meeting controls. Yes. Okay. Good. Okay. So this paper addresses the problem, which is, as we can see, long context LLM. So most of us here are probably familiar, but if you're not a giant language model nerd, they tend to, or in previous generations, they tended to, if you gave them like enough tokens to fill their whole context window. So if you like tried to maximize your usage of your favorite model, oftentimes it would just like forget about everything in the middle and then maybe get a little bit at the beginning and maybe a little bit at the end and then just hallucinate all the rest. Um, so this is a like an inference time technique to help mitigate that, among other things. Um, so the nice part about this is being that there are several ways. Obviously, like we've kind of known this is a problem for a while, but there are several ways that folks have attempted to address it. Most of which have been related to like fine tuning or like redoing the attention mask or something like that. Um, but what's nice about this is it's very like drop in. It works on inference time, and you don't have to do any extra training to make this happen. So the solution that these
Hey,
guys
Warren.
Hmm,
Yeah, I wonder if I can quick ask a quick question. Do you know
sure.
that when these models are trained,
Mhm.
are they trained with full length context? It, do you know, or are they? I guess if what I'm trying to imagine is, well, if they were trained with partial, just like recent history in the context, I could understand that. It might almost be a learned behavior, and I'm just wondering if traditionally they are trained with full length context.
Um, well, at least so with this technique specifically, it effectively like as long as you have a KV cache to play with, it'll work. So you can train
Mhm.
a model with partial context or like for short things or long things or giant documents or whatever. But if you have uh so I guess the answer would be like depending on how much and if there is anything to mitigate with how you trained your model, i.e., like you trained it for short, but you want it to still like be able to handle long.
Right.
And you can just drop this in and
And
see what happens basically, and maybe it'll help
okay,
on something like that.
gotcha.
Mhm.
Thanks.
Yeah.
Hey, Warren, is it okay if I add a little color to that?
Yeah, please do. Actually, feel free to jump in whenever, Ted. This is I know this is one of your favorites, so yeah, please feel free.
Well, I think what the question's getting at is you said that there's sort of this lost in the middle problem. And I think one of the hypotheses why we see this lost in the middle effect is because they're not really trained with long context very much. So,
Hmm.
for example, the Quen 3 model that just came out, it was 90 something percent trained with just length 4000.
Mhm.
Then they train a little bit up to 32,000, um, which is generally good enough to get it to work generally, right? There may be some lost in the middle phenomenon, but it understands. And then they use some tricks to extend rope 4 times from 32 to 128,000, and they never actually trained it even one batch between 32 and 128.
Really? I had no idea.
Interesting.
Is
It's
that
that expensive to train it, so they just don't.
is that specific to Quen? Because I know I've been sort of hearing through the grapevine that Quen like it looks great kind of on paper, and if you leave it alone, it performs great. But as soon as you try to quantize it or really do anything, it just completely falls apart. Um,
Hmm,
so the I'm curious
interesting.
if that kind of just sort of like go to 32K and then loop it 4 times, is that Quen specific, or is that like sort of the general approach as far as these days for
Uh, I I know that the general approach is you train everything short, and
mm,
then the last little
Mhm.
bit you extend. Whether they go to the full or whether they only go half or quarter of the full, I'm not sure.
hmm.
Um, but I wouldn't be surprised for the million context length if they never actually trained on it, that they trained up to half or a quarter of that and then use these rope extension tricks.
Yeah, yeah, no, that makes
Yeah.
sense.
By the way, the Quen models were traditional distilled, like Hinton, Logit's distilled.
Yeah.
So if you were trying to quantize the smaller ones, if they're less sparse because they were, you know, teacher distilled, that might be part of the reason why
Oh, yeah, yeah.
quantization is more impactful.
Hmm. Yeah, that makes sense. That makes sense. Um, yes. So, as our discussion perhaps just illustrated, there are a lot of it's a big problem. It's a known problem. There are a few different ways to do it, but the sort of core issue is that training models is expensive, and it is way, way more expensive to train like 128,000 full context runs than it is to train a 32 and then like sort of cheat it the rest of the way through because of the sort of quadratic complexity issue. Um, so, uh, thankfully, we have so like for this technique, the kind of the at least the draw for me, or like the sort of thing that's interesting to me about techniques like this is that they're kind of drop in at inference time, and I think the more of those that you can get with oh, excuse me, the more of those that you have at your disposal, the better, because if they all in the event that any of them stack with each other and they work on any model, then you can sort of squeeze out whatever you need from whatever your special purpose model is at any given time, which is a very handy thing to be able to do. So how does this work? The idea being there are two. I liked how they explained this as well because it made it very clear to me. So there's like two if it's a decoder only model, kind of the two phases are prefill and then decode. And this happens during the chunked prefill, which is like I am going to divide the chunks into fixed size chunks. Then we're going to populate the cache, and then we are going to the like try to address that quadratic complexity issue by orienting our training around a chunk prefill rather than like a big block of like pay attention to everything all the time kind of thing. Um, the I don't know if it's this part specifically, and I don't know if you guys might know. Is the chunked prefill is that similar to or is that similar to the thing that we're talking about where like we need to kind of try to reduce this quadratic complexity problem? So the way that we're going to try to cheat on attention is by using chunked prefill in VLLM, or is that just like standard best practices kind of thing? I'm curious if anybody's familiar.
Ted, do
I,
you?
yeah, I guess I would say, Warren, that there's two main benefits to chunked prefill. Um, One is when you break it up into chunks, if you're on a server with multiple users, it is
Mm,
much easier to match loads.
right.
Um, and it's much easier to mix decoding and pre-filling operations because you've got small little chunks. And so
Hmm.
it's easier to just say like, well, I'll take a couple of these, a couple of those, whatever, that kind of a thing.
Hmm, yeah.
Um, but the other thing that does happen is that if you have a very long context, let's say it's whatever, 500,000, if you hypothetically had enough memory on a GPU to load the whole thing at once, which I mean we don't, but even if you did, you would have a 500,000 by 500,000 square attention matrix that half of it is zeros, right? It's a triangular matrix.
Sure.
So half of them are zeros. So when you break it up into chunks, what you can do is you can discard the part that's all zeros. And so, for example, if you did the first 1,000 tokens, it would be 1,000 by 1,000 lower triangular, and then you could just append after you do the small attention calculation. You can append, if you physically need to, your 490,000, extra zeros at the end. But you don't have to do all the query and key junk on the full 500,000, right?
Right. Mm-hmm.
So the earlier ones, it's a lot cheaper. But then as you get towards the end, they're length 400,000, 420,000, 490,000. There's not that much difference between calculating the attention on that versus the full 500,000.
Mm-hmm.
But
yeah. Hmm. No, that is that makes a lot of sense. And yeah, is so the cool thing about this one being is that so we have like sort of a secondary way to leverage the chunks here is kind of like how I'm thinking about it, where the purpose of chunking among other things is you don't want to reprint a bunch of zeros. Well, what if you could also add useful information while you're setting up these chunks to start knocking them down, which is sort of the technique that we have here, which long story short, I guess it took a little bit to get there, but let's see if I have yeah, so here we have a little like walkthrough of what happens, and basically the idea being during that pre-fill step, let's see, we are, as procedure progresses, each sequential chunk is processed with the pre-filled past key values, and then appending an extractive information IA to each chunk, enhancing chunk specific outputs. So while we are doing this pre-fill step, we will go chunk one, and then this might be that like a margin, a note in the margin that we're making. And this is gonna, since it's inference time, this is gonna be these notes are going to be specifically query relevant. So I am in this case asking this query, and if I asked a different thing, then a model that is using this inference time technique is going to be looking for different notes to make as it does that pre-fill step. And so we have our like, yep, this is relevant. I'm going to make a note about, yep, this is relevant. And then we have like, oh, okay, this is not, such that we will have like more effectively like chances to hit the right thing as we're decoding and progressing through the rest of the corpus that we have here. I think, yeah, we have a little animation here that that is basically redundant to the previous, but O3 tried. Right? Like we also have another animation that doesn't necessarily do this, although so how attention expands chunk by chunk, is that kind of what you were getting at, Ted, with the like, okay, there's a bunch of zeros here because of all the attending that we're having to do, or is
yeah, so if you look at the top row, for example, it's got all blue boxes, but actually only the first box has non-zeros in it, everything to the right of it. So you can actually ask the attention to do a smaller problem with just the box on the left. And then if you need to resize it so that it, fits the size, you can then just like add a whole bunch of zeros to the end or whatever, right? Mm-hmm. And then the second row, it needs to be length 2. And again, whether it's actually 1 or each box represents like a unit of 1,000 or something like that or whatever, you know what I mean? Mm-hmm. but it's the height and the width are the same. So when you get towards the bottom, it is going to be, closer to the full length and less savings. But early on, you're going to get significant improvement in asking it in sending a much smaller problem to the GPU.
Mm-hmm.
Hey, Ted, can I ask a question about that? When it's you're using prefill, can we stay on that picture? Do you typically, let's see, it's sequence length, right, is the horizontal axis. So do you
Mhm.
typically do like um, a, let's say like a 16 by 16, and then you do uh, 8 more that are however many longer that would be, 24 long? In other words, are they always the same number of rows, which
Yes.
corresponds to,
So I don't know the exact implementations like in VLLM or whatever, but my assumption is it's going to use a fixed chunk size. So if it's 1,000 rows, it's going to do 1,000 at a time. If it's whatever 256, it's going to always do 256 at a time. So
okay,
it'll do the first
so
256, then the next 256, then the next, the next, the next, the next. Always the same exact number of tokens.
okay, so rather than making it kind of a variable number of rows that fits a fixed memory footprint, you think they do a fixed number of rows and that the memory footprint increases?
Yeah, like I said, I don't know, but I think
Okay,
that's what they do. Yeah.
okay,
So can also they do it in chunk because you don't want to go to memory and just fetch like few, right? You want to fetch as much as you can. So they decide based on the memory bandwidth, like what the optimal value should be.
hmm,
Checks out to me. Yeah, we've got the just sort of the pseudocode explanation of sort of how this process goes. And yeah, the thing I remember seeing something interesting here. They had a little section about or like that didn't immediately occur to me that like for this chunked prefill, there's effectively like to make these notes. Um, there's effectively like kind of a secondary stream that I might have a Zotero note about, but I'm not exactly sure. But let me see if it's like right here or not. Because I feel like it is. But the resulting output that includes the past key values continues on, and then appends an extractive instruction to each chunk, enhancing the chunk specific output. So it's sort of like as we're doing the chunk, we are also like adding this little continually increasing sort of stack of extra information without really costing us much, either very little or anything, as far as I could gather from my reading. So yeah, they have algorithms here, and they have a like a whole GitHub repo on the thing too, which is really nice. So I might go play with that later and see what else we can do. So in terms of the actual performance gains, we had a few the most notable stuff was for like small models. We had a few different evals, like Hotpot QA, I believe, was one of them. Um, and then let's see, yeah, multi-hop reasoning was over here, and we had like a 19% in multi-hop rag, and then we have a 12% in Hotpot QA. Needle retrieval also improved, but these primarily like the biggest improvements, just generally what I gathered, was that it was kind of small models get the most mileage out of this, and then larger models, you kind of get less bang for your buck as you go up. Um,
Warren, do you know how they evaluated that? Is this purely an accuracy metric that you're speaking of?
they have we have so yeah, they I think they had two kind of primary categories of the kinds of they did a total of 4 evals as I recall. And 2 were sort of orienting around the single hop, and then 2 were around the multi-hop. And then the eval task categories, they used Ruler, which I think is just like a collection of ways to rank these.
Hmm.
These things, let's see, following the Ruler task categories. And then let me see here. Uh, I kind of am tempted to just check this real quick and see, yeah, what's the real context of it if you're a long language model? So I think this synthetic examples to evaluate long context language models with configurable sequence length and task complexity. So I'm presuming that whatever metrics are being used here are the same ones that they're trying to measure on the rest of them. But I know, yeah, ruler and then sort
Mhm.
of categories were multi-step reasoning versus single hop retrieval were kind of the things that they tried to test. The other thing that is interesting here is that it's not exclusively just a performance increasing technique because those notes in the margins are actually getting produced like it's actual text and not like some like a for instance, the other inference time technique was sort of like the entropy based resample or the chain of thought prompting or chain of thought without prompting kind of. Both of those are fairly like opaque techniques. There's not really anything that you can do other than measure the end output of the model. But for this, since those notes are actually getting generated, um, you can surface them in whatever way would be, you would normally surface model output. So you can actually sort of track these notes being made in the margins as the generation happens, and so you would be able to like leverage that to A, give feedback back to users, and then B, like also collect sort of information about how that the margin notes are being made, so you can do evals on the margin note performance. Let's see. Um, let's see. So yes, stop decoding once answer confidence met. I don't know that I got to this section necessarily if this is a different section in the paper about stopping decoding once answer confidence. I didn't see too much about measuring the contract's metrics in the paper, but I didn't get all the way through it when I was trying to put the presentation together. Do you remember anything about that, Ted, from your read through? If they have like an early exit functionality, or it could be that the model was hallucinating here, so I'm not entirely certain.
Um, yeah, I seem to recall I wasn't actually all that super excited about these other use cases they talked
Hmm.
about like early stopping or showing it to users. But I did think the base technique was, like you said, it's like drop in. You can use it with any model, and that's pretty awesome.
That's interesting. Yeah, because to me, especially just because I've had like evals on the brain lately, anytime I get like an extra data point to play with, there's like a whole bunch of like levers you can pull on top of it. So I actually had sort of that was quite interesting to me, the sort of like side angles past the performance increase. Um, but the long story short, you have a sort of a number of side things that you can do with this. And it's a drop-in technique that works for whatever. Um, so we have a few future experiments, but I kind of feel like I want a little bit more. Oh yeah, here's the early exit option. Um, I kind of want, I feel like I want a little more understanding of like the technique itself more. Um, just because I see that I'm running out of slides and haven't taken up nearly enough time. Um, but the yeah, I think the interactive retrieval step is interesting to me, and sort of the RAG implications are also interesting. Um, the some and I think these are interesting next experience fine-tuned models to write margins autonomously. So I guess you could like if you are planning to always do your inference in this way, which I would be interested. Actually, I should check. I should check with the authors because the guys who wrote this paper using this technique, they also have a series of models called the Palmyra models that are specifically built to do long context retrieval. And I'm curious that if they trained Palmyra with the thought in mind that it's going to be making these margin notes, so we should train it, accordingly and try to optimize for the best kind of margin notes that we can get. Um, which could be kind of an interesting see where it goes kind of thing, at least in as far as I can tell. Um,
Can can I
yeah,
ask a question? I might have missed something here. So I'm not quite sure what this fine-tuned model is to write uh, margins autonomously. So the notes that were taken previously, those were those generated by the model?
yeah, or yeah. So as far as the understanding that I gathered was during the chunked prefill step, it is the the same model is doing the margin generation. Yeah, there's not a second model. And then the sort of the trick is that we're not like reloading the KV cache. We're just working what's with kind of already there like during our chunking step to sort of make these notes on the side. Is my understanding, but I of course could have
And
um
then, okay, so it's trained to generate notes on the side in what, in kind of a parallel stream or something
that's
in the KV cache, and then that KV cache is accessible.
yeah, I
So
so I believe so in this case or like the technique itself, since it works without training, I'm assuming there's just so like where we are just modifying how VLLM is sort of interfacing with the KV cache here. So we're doing the chunk prefill, and then rather than going immediately to like the next step towards full decode, we also make a note while we're doing that sort of chunked prefill. And then when we are doing the like we are actually answering the query now decoding step, then we have those prefills to work with is again my understanding, but my understanding is also still a little bit fuzzy. Um,
and Warren, I have a thought.
yeah.
Um, I have a couple slides showing how you turn regular attention into chunk prefill.
Hmm.
And I was thinking maybe if we tag team,
Yeah, please.
we could kind of walk through that. But then from the chunk prefill, I don't have a slide that shows it, but we can kind of talk about how writing in the margins sneaks in these extra steps.
Yeah, I think
That,
because I am quite curious about like yeah, I want to get a good understanding of like how this mechanism specifically works because yeah, I think it's a good question here, Roger, where the since this is a training agnostic technique, technically, like so if you wanted to optimize to be able to do it, like sort of how would you need to modify the training that you are going about doing? And I can't quite like get that in my head of like how I would set that up. So yeah, the that sounds like it could certainly be helpful, Ted, if you happen. I'm happy to I don't know if you can like take over for me or if I have to like hit the stop button, but feel free to
Yeah, I'm not the host, so you would have to stop
Okay.
sharing, I think.
Here, let me see if I can figure out my Zoom. Let's see. That's gonna be It's all, there we go. Okay, so we're gonna, if I stop there, okay. All right.
Cool.
Do you have perms now? Oh, let's see. We have chat. Yes, Harold, I will drop you the slides as well. It's actually just it's just an HTML file, but yeah, I'll drop it to you. Um,
Hold on. Just trying to move this out of the way. All
yeah,
right. You guys see my screen?
let's
Yeah.
see. Yeah, I
Yeah.
got
Okay. So this is like regular attention, and they're numbered 0 through 15, but like maybe if we say that each of these boxes represents 1,000 tokens, okay. So, you know, so maybe this is like 15,000 tokens of context. But so let's say these are like the manual pages for the 747 plane, and somebody has a question that's like, hey, I need to replace the whatever, the ABC part. How do I get to that? Like, what other things do I need to do, right, in order to be able to take things apart? You know, what things do I need to remove in order to get access so I can replace this ABC or something like that, right? I'm just making up a question. So, normal RAG would be you go and you hit your vector database and you get a bunch of different entries that are close matches, okay? And you stick them all into your context. That's this 15,000 tokens worth of, you know, pages from your operator or maintenance manual or whatever, right? And then after the 15,000 token, you append the question, what other things do I need to do so that I can replace the ABC part? And then you give these 15,020 odd tokens to your LLM, and it'll see all 15,000 of them, and it will, you know, it'll say, oh, well, I found some text here that says you have to remove this flap, and then you have to remove this bolt, and then voila, you can replace the ABC thing. Okay. So does that kind of make sense as just like this is setting up our RAG problem?
Sure.
Right.
Mhm.
So in regular attention, if you had a big enough GPU with enough memory, you would just take all 15,000 plus 20 odd characters from your question. And you could hypothetically, one at a time, uh, run them through your LLM, but you don't need to because we don't actually need the predictions of the next tokens because we already know what the next token is, right? We have 15,020 of them. We don't need any predictions. So what we can do is we can send all 15,020 of these tokens simultaneously in order to get the keys and the values associated with all 15,020 of those. Then for that last one, it's going to predict the 15,021st token, right? And let's say it starts with, you know, you should or whatever. So you is the next token, right? So it's going to say you is the next token. And then what you do is you append you, right? Now you have 15,021 and you say, what's the next token after that? And it says should. Okay. And then you say, what's the next token after that? So for that decode phase, you're doing one token at a time. But for this part, because you already have all the words, you don't have to do it one at a time. So that's what Warren was saying earlier. That's the difference between the pre-fill and the decoding stage. Does that make sense?
Yep.
All right. So this would be the vanilla way in which we would pass all 15,000 odd tokens in. And the way attention works is if the keys are here, okay, and the queries are here, each query token can only attend to the keys that came before it. So if you look at, for example, token query 3, when we're on the third, starting 0, the third token, it can only see the 0th, first, second, and itself keys. Okay, that's why all this stuff over here is yellow, because causal attention means you cannot attend to words that come after you. You can only attend to words that come before you. So this is a pretty expensive calculation that's approximately 15,000 by 15,000, attention calculation. All right. So what we can do to modify this calculation is we can break it up into, let's say, 4 steps. It could be any number, but let's say we do approximately 4,000 at a time instead of doing all 16,000 at once. Then if we do just this step here, which is now 4 by 16 instead of 16 by 16, and then we do step 2, step 3, step 4, and we concatenate the results, we will get the exact identical results as if we did it all at once. Anybody have any concerns whether like that we can't just break this up into rows, right? Okay. Now what I'm talking about is naively breaking this up into rows, okay? But it turns out that there's a couple of optimizations we can do. So going from this one to this one, these yellow portions out here that we know are all zeros, there's really no need to actually run through your GPU and calculate everything, because the mask says that both the queries and the keys are going to be, your end result is going to be 0. So instead of doing this big 4 by 16 calculation, you can do a 4 by 4. And here you can do a 4 by 8, here you can do a 4 by 12, and here you can do a 4 by 16. Okay, so you can see there's still some yellow. You are still doing some calculations in your giant matrix multiply that are kind of unnecessary because they're going to get masked out and turned into zeros anyway, but a lot less. And so again, if you have one user, it doesn't really, I don't think, matter if you save. But if you have multiple users, then you can pair some of these cheap step 1s for one user with an expensive step 4 for a different user, and you can kind of optimize your GPU utilization.
Yeah, no, that makes a lot of sense to me. I think, let's see.
Okay, so then this is optimizing the length, but the way I've written it, we're still naively calculating the key for token 0 4 times. We're calculating it once and using it up here. Then we're calculating it again and using it for this set of 4. And then we're calculating it again and using it for this set. And then we're calculating it again and using it for this set. So that's not like super efficient. So what we can do is, once we do step 1 and we know the value of the keys and values, we can save them somewhere, and that's where the KV cache comes in. So chunked prefill says these light blue squares are the same exact keys and values that I had in the previous step. So I will just simply load them instead of recalculating them from scratch. And then once I've calculated these dark blue ones, I can then append and my KV cache gets bigger. And now I have all these light blue ones. And once I've calculated these, I append them and my KV cache gets even bigger. And so when we're all done, we're going to have all the way up through, I'm going to go back to my original numbering, all the way up to 15,000 something, okay? All loaded in the KV, ready to be used, sitting in a KV cache somewhere. And now we can go to decoding mode, 1 token at a time. And it says, you should first do this, then do that, blah, blah. So this is just regular chunked prefill. This has nothing to do with writing the margins, but does this part make sense?
Yeah, no, that's super helpful. I think to me, is this I guess or I'm curious how you like, where did you get is there a paper that you got this from specifically, or is this just sort of a general
No, I read about this, and I actually used Excel to create this graphic.
Yeah. Very nice.
because I'm a dinosaur and I don't know how to use these new tools.
Perfect.
So yeah. So then where writing in the margins comes in is, after step 1, we have all of these sitting in the KV cache. Okay. Normally, you just immediately proceed to step 2, where you take this KV cache and you start calculating the next bunch of keys, and then you'll have this bigger chunk, and so on and so forth. But writing in the margins says is, before we move on to calculating the next set of keys and values, I'm going to sneak in a decoding step. Okay. So if you recall, my question was, how do I get to the ABC part in my 747? So what they do is they take this KV cache, which let's say it's 4,000 tokens. They do a little bit of extra work to, I don't know the exact details of whether you're using prefill or decoding, whatever, but they append onto it a question, something of the form, in the text you've seen so far, does it talk about anything about how you would answer the question? And then they paste in the question, how do I get to the ABC part so I can replace it?
Interesting.
Okay. So the prompt is something along the lines of, did you see any text that relates to paste in the user's question? Okay. And so then what's going to happen is the LLM is going to answer, no, this first 4,000 is just like the table of contents of the user manual, and it says this and that, and it's talking about tools, but it doesn't mention anything about this ABC part. Okay. That's your margin note. No, I didn't see anything.
So Ted, am I understanding this right then? So we've got this long sequence that we're in the process of doing chunk prefill. This
Yeah.
long sequence came from someplace, some sort of context, RAG or otherwise.
Yeah.
And while we are going through doing the chunking, we're actually inserting into that same sequence a prompt and then
Yes.
generating for a bit some
Yes.
like
So
one
step
token
one and a half
one token
is,
at a time for whatever that right in the
yeah,
margin is, and then we
yeah,
go back to a prefill.
yes. So step
Okay.
one and a half is what you just said, where we sneak in this prompt that says, have you seen any text that has to do with user question? Okay. And then you let the LLM actually do inference. You do decoding and it says whatever. So now what happens is we were at token 4,000 when we did the step one of the prefill, right? We're not there anymore because we inserted this little question that's 30 tokens, and then the LLM answered it for like another, let's say, 50 tokens. So now we're at 4,080 instead of at 4,000.
Mm-hmm.
This is the crux of the writing in the margins paper. They said none of the first 4,000 items in the KV cache have changed. We simply added onto it, but we haven't modified any of the first 4,000. They're read only. Okay. Mm-hmm. So we can literally truncate the last 80 tokens in the KV cache, and it will be as if we never did this extra step one and a half. No one will be the wiser.
Wait, where did the response go?
You have to copy the response from the LLM into somewhere into main CPU memory and save it off.
Okay.
But you stash it away and then you truncate the KV cache, and it's as if you never did writing in the margins. It looks exactly like normal chunk prefill. You go on to step two as if nothing ever happened.
Okay, I get that, but I'm wondering what happened to the writing in the margins.
No, so you got the margin. You got the margin, okay? But the margin was cheap because the KV cache was already filled.
Yep.
Then what you do is you do step two, and now your thing is longer. And now you repeat the exact same process. In step two and a half, you say, hey, have you seen anything in the text that has to do with part ABC, user question? And then the LLM says, well, actually, I thought I saw something about whenever you need to do maintenance on the wheels, you should first do XYZ, which is actually a bad margin. It's actually trying to help you, but it was a mistake. Okay, it was not actually related to part ABC, and you do it after step three, and then in this chunk, we're very fortunate. It actually says, hey, this is how you get to part ABC. First, you remove panel 9, then you do this, and then you can get to part ABC. And so because this text is no longer in the middle, it can't be lost in the middle. It's the text that's right there. It's the most recent thing that we've seen. Yeah. Now, when you append this step 3.5, the LLM is likely to get it right and say, I just saw this text that says remove panel 9 and do this. And that's what you need to do in order to get to part ABC. And you save that off. And so for every chunk, you save off these margins, okay? Naively, you could concatenate all the margins. They did an extra step where they evaluated which of the margins seem helpful and which seem unhelpful. And that pared it down by dramatically because it ended up that far, the vast majority of the margins were not helpful.
Okay. And now do they insert those notes or pared down notes?
Yes.
Finally, they insert that in before the actual question.
Yes. And so in normal RAG, you would say, here's my 16,000 tokens that I retrieved. Now the user question is, how do I replace the ABC part or whatever, right? Instead, what you do is 16,000 tokens, paste all the useful margins only in there. Then say, how do I replace the ABC? And in theory, all the correct answers are now going to be repeated because they're going to be back here where they were in the main text, but they're also going to be referenced in a margin. And so by being doubled up, it increases the odds dramatically that you get the right answer, both because this one's really close and because it's literally twice.
So you're somewhat putting like a weighting bias on it then.
It's a recency and a weighting bias. You get both benefits.
Oh, okay. Yeah, you get recency because it's at the end, and the weighting bias because it's in there multiple times.
Yes. Now, the reason why writing in the margins is so cool is because people have tried this before, except what they did was not this cool KV cache thing. They simply took each of the chunks that came from your vector database and they said, summarize this chunk, which costs you a full cost LLM inference of that chunk. So if that chunk is 4,000 tokens, for however many of those you have, every one of those is a full cost 4,000 plus your question, LLM step. Here, it's not a 4,000 plus whatever your question is. It's only a whatever your question is because the first 4,000 is already sitting there in the KV cache waiting for somebody to start doing decoding on it. It's not free. It's not even remotely free, but I think they said in the paper that this is useful when your RAG is 16,000, 50,000, 100,000, 800,000. It would not make sense to do this writing in the margins technique to ask it, what's the capital of France? Right? Because you're adding a whole lot of overhead with these margin things for a 10 token question, right? But if you have a 50,000 RAG retrieval and your question is only 30 tokens long, the relative cost of doing an extra step 1A is quite small. 30 tokens here and then a little bit of whatever it answers. So, you're generating maybe 100 tokens.
So it seems like this is kind of equivalent to asking a question at the end of this big prefill can lose stuff in the middle. So instead, we'll ask the question a whole bunch of times for each chunk.
In a way that is super compute economical.
Yeah.
Yes. Yeah. Because you could have not done this naively. You could have said, let me just plop one RAG chunk in and ask the question, and then a second RAG chunk and ask the question, and a third RAG chunk and ask, right? You could have done that naively without using the KV cache, and it would be like quadratic cost.
Yeah. I'm thinking through, Ted, in my back of my head, the games we were playing with the that would fit into this as well, as you could.
Oh,
you
really?
could prompt.
We got another one we can stack on here? Hell
yeah. Yeah. Well, it's
no. So this is where my inspiration came. I read writing in the margins, and that's when I said, oh, you can play with things on the KV cache with masks, and you could thereby do a beam search by just clever bookkeeping on your KV cache.
So instead of going into this, sorry, go ahead.
I was just going to mention. I was looking at Appendix A. Did you happen to catch that one, Ted? Where they're like, in theory or in applying this in a RAG context, um, they sort of detail some further experiments in which you would decouple the margin generation step from the margin classification step. So the so we have our chunk, and then we have our we are or yeah. So it was sort of out of order in the graphic, but I believe it is we have our chunk and then we have a short classifier like of relevancy, like yes, no. And then we have our it's not parallel decoding, but it's the like IA extra extractive instruction, which I'm like a little fuzzy on exactly how they're doing that, but they got that decoder step so they can add the actual note, but they are using so what they did was batch it all together, where you have chunk, you have classify, then you have decode, then you have chunk again. But if you were to decouple the generation from the classification, and then you could, so sort of the advantage that you get from doing this little loop is like as we've mentioned with the chunked prefill, because we're cutting all that extra stuff off. Like it could be quite good for parallel optimizations. So in this case, if you were to decouple it even further and say, like, oh, I'm going to have, I'm going to try and offload our classification to like CPU or something, but still, and then like also treat the generation step separately from that, then you could sort of mix and match between all of these sort of sub steps on top, while like without having to like refill our or like by working with our currently filled or currently pre-filled KV cache already. So the that sort of stuff is outlined in Appendix A primarily. I actually I have like a notebook LM going on the side here, so I've got a couple of like
Yeah.
further notes too. But yeah,
If I remember right, I've been talking about you sneak something in as step 1.5, two and
Mhm.
a half, 3.5, 4.5. Okay. Um, Once you have all these margins, if you want to do the step of deciding which ones are relevant, okay, if I remember right, the main paper says just do that as a completely separate LLM inference step where you concatenate them and say which of these are useful, or you do it one at a time, or whatever you do. But because the margins are relatively short and whatnot, you can just do those. Theoretically, you could do this as like another step 4B, where you just append stuff on here and ask the question, do some decoding, and then you can just rewind back as if it never happened. But if you do that, the convenient thing is you don't need a second LM. The inconvenient thing is that you do have a relatively long context here. So decoding steps here are a little bit more expensive.
The what I posted actually put the thing in the chat. I'm not sure if this runs counter to that observation, but we have a excerpt is on page 3, and it says it is possible to use the same instance of the model for both generating the margins and classifying without affecting the pre-filled KV cache. So does that indicate that we have maybe just like a set? Well, no, because we have the same instance of the model, right? So in this case,
That's
Yeah,
it's sounding
you
like
have a lot of choices here, but
Mhm.
my understanding is that the KV cache is still in a multi-user system. The KV cache does not necessarily persist between token generations. In theory, that's the most efficient thing, right? So in a
Mhm.
single user system, you would just say like keep adding one token and keep doing decoding. But on a multi-user system, it's my understanding is you just don't have that benefit. So you're like constantly loading the KV cache,
Hmm.
um, and you could be loading it for a different user, or you could be loading it for yourself user for just a different prompt. And it's kind of six of one, half a dozen the other, whatever, you
Mhm.
know. Um, But it kind of doesn't matter because if you are that kind of service provider, you probably have multiple servers and multiple models. So to me, it doesn't really make a difference whether you use the same model or you use a cheaper model because you don't really need a super powered LLM. You're like, tiny LLM is smart enough to just say like, does this block of text have anything to do with part ABC?
Sure. Well, yeah, and I think most of the evals or the classifiers do like LLM as judgment in some fashion or another. But I almost feel like you could get away with even like a non-generative neural network that's like purely classifying these like
Oh,
relevancy sort of things as well and try to
you
scoop it up.
probably could, yeah,
You
yeah.
know.
Can I ask a question?
Mhm.
Well, so the way I see it is it's sort of like online summarization, right? You have like first 4,000 tokens and you summarize them, then you have next 4,000 and you summarize them. And at the end, like you enhance the tokens that are like relevant, right? But what you could do is like you take the first 4,000 tokens, summarize them, save them somewhere for all the 4,000 chunks of tokens or whatever the chunk size you wish. And then you can just like query through those like summarized version of tokens in the same way and get, oh, this part is actually the most relevant. And then you can fetch only that part and answer that question. Wouldn't that make more sense?
That's
Like,
cool. Yeah. Yeah. So theoretically, if the margins were perfect, I think the issue they have is the margins aren't perfect. If the
okay,
margins were perfect and you basically had like no, no, yes, no, then you could say, well, screw all that other stuff. Let me just grab chunk three and do rag on that. I think that's what you're saying, right?
yes, yes. And you
Yeah.
can all pre-process that stuff, right?
Yeah. I think if the margins were perfect, I don't think that they thought they were in the example, which they have to shorten the examples for the paper, but they were talking about not me with my like plane thing, but it was like a question about a novel, and they're like, what kind of room or whatever, and so the margin didn't really have all the facts. It still needed you know that chunk, and so the way they were thinking about it is we'll just augment RAG with this recency frequency margin stuff here, but ultimately some of the time it is going to have to go all the way back here
But
to
yeah.
find stuff. Um,
And
but if
potentially
you
the
were if you were that confident in your margins when they said no, there's nothing here, then yeah, I guess you could actually get rid of those chunks.
If you're like only training for, let's say, like your company's information or something, then you can like divide the documents in a way that like your margins can be perfect, right? So
Well,
each
can I ask you a
the
question when we
the,
say
the, the
margins perfect?
margins. One thing that to be clear, sorry, Roger, before we go on, one thing to be clear is in this technique, the margins are question specific. So people have tried to save summaries of each chunk in
Right.
advance, but the problem is the summaries are not specific to your question, and therefore the summaries are not necessarily helpful.
okay, that makes sense. That makes sense.
Yeah, that's what I was wondering. Is this writing in the notes being perfect or in the margins being perfect? What does that mean? Are we assuming that all the information is in the note, in the margin, or just that it has kind of create some sort of reference back to the original context? And it sounds like Ted, it's the note isn't standalone. The note helps you get to the right information.
Yeah, and maybe I should stop sharing and let you bring the paper back up, Warren. But that's
Yep.
what I recall is that the notes aren't meant to be 100% extractive of everything you need from that chunk.
Yeah, I think
Ted,
I remember I remember something where I was just looking for the passage, but I feel like they actually did do some amount of testing on this where they tried it with like generate the margin notes and then only keep the ones that the notes said was actually relevant and then don't include the notes or like do like only there was some configuration where they said actually the best performance that we got was when we send like both the retrieved classified chunk and the margin note, and our performance is worse if we only use like just the relevant chunk and or just the margin note
It
for
makes
the
sense.
Yeah, I
something.
think you're right. I think
Yeah.
there was an ablation in there. The other thing that I was a little confused about at first is chunked prefill is really part of your inference server implementation. Okay.
Mhm.
So um, if you think about this chunk as being the first RAG document, and this as being the second RAG document, and the third RAG document, it opens up the possibility for other kinds of indexing and things like this. But the reality is the chunked prefill that, say, VLLM does for you is utterly independent of your RAG solution. So your first document might be 11,015 tokens, and your next RAG document might be only 3,400 tokens. And then the next one might be 26,000 tokens. So these chunks do not correspond to RAG documents. These are just every 4,000.
Mhm.
VLM is just doing chunks. And so sometimes this could be smaller, sometimes this could be bigger than a RAG document. And that's one of the reasons why, if you look at the exact wording of the, when I call this step 1A, the 1.5, this prompt, it's kind of it's a little bit more broad. It's not like, hey, give me the exact summary, whatever, of this chunk, because this chunk is not necessarily a unit. It could start in the middle of a sentence, and it could end in the middle of the sentence, and it could be kind of arbitrary, and it could even split where half of it is the end of one RAG document and the other half is the beginning of the next RAG document. So you do have to understand that these margin notes that it's making are not on nice atomic semantic chunks.
Mhm. No, that makes sense. Yeah, I could see it like getting garbled if it's like dropping too many things. It's kind of what
Hey,
I.
Ted, can you leave that up for a second?
Okay, yeah.
Yeah, I wanted to kind of finish the comment about the beam search optimization
Oh,
that we did.
Mhm.
So right now, if I'm understanding the way they're doing it, they'll kind of do a pre-fill and then do a little bit of generative stuff, back up the KV cache, do a pre-fill, do some generative for the notes, back up a little, et cetera, do that repeatedly. When you start playing with the position encoding and masking that we did in the beam search, you could essentially do a standard prefill and then do our little beam search trick to generate all of those margin notes in
Ooh.
one pass instead of having to go into generative cycle, multiple times where I think it's going to be slower, right? Because one token at a time, you have to do a full pass. We could do it where we could generate all of the notes in a single generative cycle.
yeah. So we're doing decoding for all beams at once.
Right. And each
It's
beam,
not, in my mind, it's not immediately obvious from writing in the margins to go do a beam search. It does require a little bit of different fiddling, but the idea that old portions of the KV cache never change and can be reused, that's
so
to me, that's the thing that I'm most standing on the shoulders of the writing and margins people.
so when we're talking about beam search here, though, each of those beams is referencing back to a specific pre-filled chunk and the KV cache before it. Right. They're
And
not all beams from the same place. They're actually beams from a different beam for each chunk. Does that make
I'm not
sense?
I'm not quite sure what you're saying. I mean, when you very first start the beam search, whatever context there is will be the same shared.
Right. So I'm only using beam search that's what the terminology we were using when we were playing with the masking and position information. So what I'm saying is when you're in a generative phase, we could have that same question 4 times, and each one has a different history mask. So it knows like what part of the history I can reference. So one instance of that question, one generative, we're generating 4 responses simultaneously. One of those generations only looks at the information from the first chunk. The next one references, and by the way, the position encoding it's right after that chunk,
Yeah.
right? And then we do it, the next one that's being generated uses all the history up through the second chunk, and its position thinks it's right after the second chunk.
That's right. Yeah. Yeah.
But all this
So
is done in one
there's
pass.
there's no mask and position encoding math in writing in the margins. They only do regular
Yeah.
sequential decoding.
Yeah.
But if you, in my mind, as soon as you sort of entertain this idea of flexibility, then you can do multiple at once, like you were describing, Roger. And you can also do this idea of compaction, where if you have dead branches of the beam search, you can literally remove them from the KV cache, and you can compact
if we
things
were,
to the left.
That's if you're doing kind of a rolling beam search or something. Yeah. I'm talking about just using that same trick to generate 4 notes in the margin simultaneously, and do that so that you don't have to stop and do generative for a while, then prefill, then stop and do generative for a while. Just do the whole prefill and then do one cycle of generative, and but each one of those generative ones thinks it's at a particular point in the history in the KB cache.
Oh, I was not tracking, but now I understand what you're saying.
Hmm.
So hypothetically, you could wait until OE gets to step 4.
Yep.
And you could say, write me a margin on chunk 1, and then to the right of that, write me a margin on chunk 2, and to the right of that, write me a margin on chunk 3. And then they would all complete in parallel using our beam technology.
Yep.
Very cool.
Yeah. Anyhow, I just wanted to use the picture for that. I'm going to add that to our VSLM list.
Ooh, yeah, good call.
That's gnarly.
They let's see. Well, and I think so they have section 8 and 9 of the paper that I was just looking at. Let's see if okay, good. I got a thing here. Let's see if I can find. I think it should be this. Yeah, I think. Is that gonna do it? Okay, yeah. On the topic, this is good, but we'll do that in just a second. But I saw they mentioned something about there's something like fusion and decoder about that. So like there's a lot of fusion. Yeah. So it's like up here. Yeah. Okay. So future directions being optimizing computational costs through better KV cache management and improving baseline models performance by fine-tuning models specifically for the extraction and classification tasks. A further improvement could be also determining the optimal segment size, which could be different from each model. So would that would be the optimal when they say segment size here, this would be different from the pre-filled chunk size, yes? Or are they talking about the same thing?
I don't know which they're talking about off the top of my head, but theoretically, both of them. You could say if my chunk prefill is 4,000, then maybe certain sizes of RAG document work better. You know?
Right. Okay. Yeah.
Yeah, but the more obvious answer is just you're doing chunk prefill. What is your chunk size? If the chunk is really small, writing in the margins probably gets to be a little less efficient because you're constantly calling it over and over again.
Mm-hmm. Let's see. And then we imagine our inference pattern would be a good choice for transformers performing attention in segmented context windows instead of accessing the whole sequence. So like sliding window stuff here, or well, and I guess
kind of what it sounds like.
That's basically what Roger.
Yeah.
Well, this is slightly different.
What Roger was saying.
This seems a little different. They're saying that when I ask the question in it after chunk 3, don't give it the entire KV cache all the way back to the beginning. Just give it the stuff near chunk 3. That's the way I'm interpreting that.
Right, which is kind of like what a variant of kind of of what you're saying. But in particular, they're saying if you're doing that kind of sliding window anyway, then you can use that same window as your window for what you write a margin about.
Right.
Cool.
Yeah, I made a couple of extra little notes here. I wonder if anything's like particularly relevant. On how might this was the last one was oh yeah, this one was about the ablation stuff. So I'm interested to see if there's anything new here. Um so we have the no margins filter. So two main ablation studies, no margins filtering, which we excluded the classifier from the pipeline and all of the summaries went in. So that decreased accuracy makes sense. Negative instruction manipulations, filtering margins is crucial. Okay, yeah, that's straightforward to me. And then we have where in the final step, the original full context was entirely replaced by only the extracted positive. Which I think is, yeah, so like Erd, I think that is basically what you were describing, right? Where it's once we have classified, let's throw it in the garbage kind of thing, if it's not good. Um, what was found? Results for the approach were mixed across models and tasks. For most, incorporating both was max performance. Only content for margins yield varied results. Some went down, remain consistent, and then phi experienced a slight increase. I'm curious. I'm curious if that holds to phi 4, and then B, I'm curious if that holds to phi 4 reasoning, both models, and then C, I am curious why did any of those results come up the way they did, specifically with phi. Just because I know it's the as I recall, Phi is Microsoft's like basically their effort for it is to try and make the tokens that they're training on as high quality as possible. Because I think that the origin is the textbooks are all you need. So I'm curious if so if you use really good baseline data, then maybe like only throwing out or only keeping the best of the best of something that's already sort of like pre-curated is maybe kind of why it's getting the edge there. Or might okay, outcome might depend on the specific task. Retaining, but yeah, so end of the day, um it is it seems like including everything is best. And we would so relevant margins plus full context, and then how I might leverage some of the things we discuss here in the context of sliding window attention. And or I wonder if I can describe in a way a language model is going to recognize the beam search like hybrid decode thing that you guys are describing. I don't know if it'll I can't think of like a collection of words that it's going to be able to conceptualize this with. Let's just see what it says with sliding window attention. The other thing I'm kind of curious about is let's see. I want to I need to drag this or hide this. Okay.
We'll see what the model says, but for sliding window attention, you would think writing in the margins could be super helpful because you now physically don't have access to the earlier RAG chunks. So by getting all the summaries really close to fit in your current sliding window, sounds to me like this is going to be a huge win.
Right. Um, okay, so yes, so
But
Notebook
Ted,
Element is very insistent on sticking to the text. Yeah, go ahead. Go ahead. You're good.
well, I was just going to say the thing about these writing the margins is that the notes in the margins are only applicable to a single question, right? So each time you do a question, you'd have to go through your sliding window and do the generative cycle. Yeah. Okay.
Yeah, so a more general idea, like if you imagine an SAT test where you read a page of text and then they have four questions that are about that same content, right? Writing the margins doesn't really work because to your point, you'd have to recreate the margins four different times for each of the different questions.
unless you use our trick, in which means you're just
Oh,
using
actually, yeah. If you know all four questions at once, you can create four margins all at once as you do your chunked
you could also do
pre-fill.
that. You could
You
also
can
do
do
that.
that. But
But even if
in
they're sequential,
a whatever world where you don't know what the next question is going to be, then you would incur this penalty of reprocessing all the text.
but if you're using our trick, you're going to pre-fill the cache once, and then you're going to do this parallel note-taking, margin note-taking for this question, and then you can go to the next question and pre-fill with notes in the margin for that question. That long context KV cache doesn't change. You don't have to do anything.
You're saying just by using some masks?
Yeah, just using mask and position stuff. You can just do it for each question. Think of it as kind of a KV cache scan that you do before you answer the question.
I like it. I actually think that rather than doing this fancy chunked pre-fill thing, you could just do it as a beam completion.
Yep.
And that would give you the freedom then not being stuck to the chunk sizes.
Yep.
So you could have arbitrary, and so you could, for example, purposefully keep track of and align your masks to the actual RAG document boundaries.
Yep.
And so you could have your margins really be much more semantically meaningful. And as soon as, so Roger, we just need to make multi-decode the norm.
Yep.
Where you say, if you know you're going to ask four questions, don't ask them one at a time. Paste them all in, and we'll do four simultaneous decodes with masks so that the questions don't see each other. They just see the content that you want the question to be related to.
Yep.
All right. Multi-decode paper for this year's NeurIPS.
Yeah. Well, I was actually, it's fun. So when I was grabbing my notebook LM, but I have the other, I still have my leftover notebook from when we did Entropics that has, I think, like 3 or 4 other papers that are all based kind of orienting around the sampler step. So what I'm probably going to do after this is, make another note and then throw all of these into the Entropics notebook and then see what I come up with, in terms of aggregating everything together.
The cool thing is with multi-decode is if it becomes the norm, I don't know how often this comes up, but if you know that you have 4 questions you want to ask about something,
right?
OpenAI can probably do this 4-way decoding at about half the cost if you just asked one question, then the next, then the next, then the next. Because you're getting 4 tokens for every forward pass.
Yep.
Ooh, okay, there's some implications there. What if the user is not generating the query? What if I am just observing the user and attempting to generate as many in theory useful queries as they might look to me to expect?
So that's speculative decoding, not at the token level, but at the full query level.
Yep.
So you take spam it through
are you building a data set then? So that when you see this same type thing come along?
Well, I mean, it's essentially yes, and I suspect that's fine. That Sam has also it's also finally occurred to him that chatbots are stupid, and it's
It took this long.
that it's much more interesting to have a proactive assistant than a reactive one. So the sort of core of a system like that is I am just watching and I'm going to try to guess what question you're going to ask, and I'm just going to do that all the time. And see what pops out.
Yep.
After that.
So do you think that the reasoning, when you're reasoning along multiple dimensions, you can reason in parallel like that, what you're
That's
saying?
interesting too.
Should be able to.
Yeah.
It just depends on whether your questions build on themselves or if they're truly parallel, right? So if you have a whole bunch of information about a car and you just want to ask it something about the engine, you want to ask it something about the brakes, and you want to ask it something about the airbags, there's no reason why you can't ask those all in parallel, right? But if your questions are more like, and what if Sally bought three more apples? And what if Sally doubled the number of her apples? And then what if Sally gave away 10 more? Then obviously there's sequential, that there's a dependency. And so you would have to do them sequentially. Does that answer your question, Dave?
Yes, Ted, and I'm sorry, as always, I was distracted, but I really apologize. I didn't hear everything.
So Ted, it seems like I could see kind of this, you get wide independent chains of thought, and then there's some sort of combining, and then they go off independent, and then they kind of combine.
Yeah, you could, if you do parallel decoding,
Yeah,
multi-decoding, you could then allow all of them to be visible in the context for the next round of questions.
yeah, exactly.
You
Yeah,
could say, okay, yeah, now they can all see each other. But
yep.
they don't see each other initially just because you don't want word
right.
fragments and sentence fragments and things like
Right.
that.
Yep.
Let's see.
And then, yeah, just like having a small model that's deciding is this useful or not, you can have a small model deciding, do I need cross feeding between these decodes
Right.
or not? Yeah. Interesting.
Let's see. Trying to mathematical foundation. I wanted to see edge cases, production, and then related work. Okay.
What are we looking at? This is
Sure.
the
Yes.
paper?
Yeah, so this is the prep work that I was doing here.
Okay.
This is Claude 4 Opus, though. This is Mr. I came out today and I'm the biggest guy, and I'm only going to give you 3 queries for the next 3 hours. He gave me some speaker notes that are actually kind of interesting. It was because I remembered something about, it was like what you guys were just talking about. I feel like one of the models said something about it, and it made me think of the paper, but I can't remember what it was now. But oh yeah, I wanted to try and see, can you guys hear this? Let me see if this is gonna work.
Okay, let's unpack this. You know that feeling when you're trying to get...
Is that audible to you guys?
Yeah.
Yeah.
Okay.
Yeah, it's just fine.
So what we can do is we can go here,
information out of a really long report or document.
and then we can say,
Want to share your thoughts on this?
yes, I do. We're actually going through this paper as a group right now, and we are thinking about some of these techniques in the context of sliding window attention. What are your thoughts? Oh wait, was my microphone not on? Let's see.
No, it was. Still is.
Okay, is it? Let's see. Is there like a submit button? Okay.
Oh, hey there. No worries at all. Take your time.
We're just getting started, so you haven't missed much. Is everything working on your end now?
Yeah, no submit. Yeah,
Okay. Now we're gonna try. We're going through this paper as a group. Can you guys tell us about what your thoughts are in the context of this paper and sliding window attention? Okay. Now they should talk.
Oh, great to hear you. Yeah, so we're just diving into this paper, writing in the margins.
And it's all about how to help large language models better handle really long documents.
Your question about sliding window attention is interesting. That's another technique that tries to deal with long contexts.
Exactly. Sliding window attention limits how far back a model can see in the text at any given point.
So instead of looking at the whole thing, it's just looking at a chunk. and that window slides along.
It can help with computational costs, definitely. But the writing in the margins approach we're looking at takes a different tack. Instead of restricting the attention window, it's about augmenting the model's processing with these intermediate margin notes.
Think of it like, instead of just squinting harder through it.
I'm not thrilled with this. We've already covered this part, but I want to see if actually let me do another one so that we have that. But yeah, I just wanted to like try that and see if it was a thing. I feel like there's probably a way to do this.
What is this that you're running?
Oh, are you not familiar with this? This is Notebook LM from Google. Did you have you guys for those who aren't familiar, if anybody has heard like those podcasts that sound like that, specifically with those two people talking, like this is where they come from.
Find it so grating. Like I just want to punch. I want to punch that lady.
They are kind of getting on my nerves at this point too. Just
She seems a little condescending, you know.
They and occasionally they make very weird noises too, which is kind of fun. But they just added the like interactive conversation, and I'm suspecting that maybe, or like I'm hoping that there's a workflow in there that's actually like quite I don't know, useful in some way. But my primary reason I like this is because I can take like 8 bazillion sources and turn them on and off, and then say, make me a study guide about it, or make me a mind map about it.
Well, that sounds useful as far as just not a tutor, but a guide, I guess, through the information.
Well, yeah, it's like so in this case, we had it generate a mind map, and then obviously we have like okay, here's a bunch of questions that you could in theory ask, which is actually, so this one's quite relevant here, which is like, here is our breakdown of chunked prefill. So this actually could be a good tool for like a post discussion thing. So you take a paper, you throw it in here, you generate the mind map, and then as questions or discussions come up, then you can find the corresponding concept and then just click the prompt. So you don't have to like type in such, and you can just sort of look and then click while people are talking, so you don't have to mess up your flow.
Cool.
And then yes, but okay, let's see. Yeah, I'll probably have to try that a little bit more on my own, because I think there's something there where it's like, okay, if we could do this with 8 people and then also a couple of robots at the same time, I think that could be kind of fun. But let's see.
Well, we're at time. Did we get did we get where we wanted to be?
Yeah, perfect. I mean, I was just running out of stuff, so.
Oh, okay. Yeah, you do something that Ted knows, and you can get a lot of filler. Apparently, is the net. Thank you, Ted.
Let's see. Let's end this.
So is the summary about this then that it's effectively using KV cache, and it combines both these note in the margin with the full context, and that's why it works so well?
The big trick is that they can rewind to make it look as if you never did step 1A decoding, right? And then the other parts have been done before, but expensively. And they're doing it inexpensively in terms of creating margins and in terms of sticking them at the end before they tack on the user's actual question.
Gotcha.
So I mean, yeah, it's hard to say. There's so many papers out there, so many things people have tried to say like exactly how this differs from everything before. But what makes this most feasible is how inexpensive it is compute-wise, the way they use the KB cache. Otherwise, just creating summaries of chunks is not terribly novel.
Cool.